Compared to other distributions, such as the Bernoulli or geometric distribution, this Poisson distribution is slightly, marginally, maybe difficult to understand. So I'm going to go it in a couple of steps, and I think the derivation in your textbook is the one which I found out to be the easiest to understand. So let's go over Poisson distribution. Now, what makes Poisson distribution different than other discrete probability distributions is the fact that in the other discrete probability distributions, we had trials. Think about Bernoulli trials, and each trial ends as either a success or failure. Here, a similar picture is also present in Poisson distribution. On the other hand, it is difficult to identify trials in Poisson distribution. What do I mean by that? Let me just dive into an example, and let's see how we can relate it to Bernoulli distribution and other discrete distributions. Let's say that we have we are employed in a company which takes phone calls, and what we would know in such a process, I may say, is the rate of coming phone calls. And we can describe the process by using a relation such as this one. Rate, which let's show it with lambda, is going to be equal to 3 phone calls per hour, right? How can you find this value? We can use relative frequency interpretation of probability. For instance, in the history for the last couple of years, of course, it's not going to be infinite, but for a long period of time, we are going to write down the accounts related with the phone calls. Then we are going to find an average value for the number of phone calls per hour. And let's say we would like to estimate the number of phone calls in 2 hours. So in this case, we would say that we would think about that, the whole thing as if we define x to be equal to total number of calls in time t, which for this specific example, we equated to 2 hours. Since the rate of phone calls is 3 phone calls per hour, then we are going to multiply this rate, lambda, by the time duration, and we can find the expected number of calls. So if in this company, let's say that this is day 1, you start working here and you ask your working buddy and ask him or her, what is the average number of calls in 1 hour? He or she says that it is 3 phone calls per hour, right? Then let's say that in that first day, you have something else to do for some 2 hours period, and you would like to have a reliable estimate of number of phone calls during that 2 hours. It's going to be 2 times 3, 6 calls during these 2 hour period. Note that this calculation, this 3 times 2 is 6, didn't depend on any probability distribution. It was more like using our logic. We came up with this result. So whatever the rate is, we multiply by the time t that we consider, and we find the expected value of calls. Now the question is, what is the process going on here, and can we find a more formal representation of the probabilistic description of this process? Now let's also just talk about this x a little bit more. What can this x be equal to? Note that x may be equal to total number of calls in time t, right? I'm not talking about the expected value, but if you wait for any 2 hours, it is possible that you may have 0 calls. It is possible that you have 1 calls, 2, 3, it goes like this. And there is not an upper limit here. So the random variable that we talk about is actually an countable infinite series. So therefore this is going to be a discrete random variable, because it's going to be forming a countable infinite series. So it's like geometric distribution, but unlike geometric distribution, 0 is also an outcome or an element of this set. So now the question is, what is the distribution of this X? So the number of phone calls during any time hour stay. You may say that, okay, didn't we have already found that? Actually, no, we have only found, using our logic, the expected value of calls during T hours. We would like to find, the probability mass function. So this is very much different from the derivations related with the other discrete probability distributions. In those probability distributions, we started with fx, right, in binomial, in geometric. Then we have derived expected value of x, variance of x. Here we start with expected value of x using our heuristics. Then from this point, we would like to travel to or move to probability mass function of x. Let's see. Now, the second step, we are going to approximate this process as a Bernoulli process. How can we do that? Actually, why do we want to do that? First of all, the motivation may be necessary because we got a well-built formulation for Bernoulli process. Discrete events, one after another. Each of these events may be failure or success, failure of success. So these number of events is the Bernoulli process. So depending on different aspects of this process, we can use binomial distribution or geometric distribution. All right, so now how can we change this into Bernoulli process? In Bernoulli process, we have trials, 1 to n. Here, actually, we don't have trials because what we can call as a trial is actually continuous time here. There is a continuous time, and we cannot say that there is one time here that may occur, that may, a trial may occur here and here, so that these trials may end up either as a call or no call kind of thing. So one cannot directly say that, but maybe we can liken it to such a process. So in order to do that, what we do is we just draw a real axis which is going to represent some portion of the real axis, which is going to represent the time segment that we are interested in, that 2 hours, for instance. Then what we are going to do is the tricky part about this derivation. We are going to divide this segment of t into very small delta t. Each of these time intervals will be equal to delta t, but delta t is going to be very, very small. In this case, how many of these delta t's do we have here? It's going to be n, the number of delta t's here, t, the total time, divided by that small delta t. How much small I haven't talked about, I'll come to that in a minute. So now, when we actually divide those two, it's going to be number of delta t's. And now here is the trick. I'm going to call this number of trials. So let's complete the analogy. In each of these delta t will correspond to a single trial. So maybe naturally these, in a continuous time, we won't have these trials one after another because time is continuous, right? But on the other hand, when you make delta t small, then you can, so the processes will be like that. There is one trial here, and what trial this may be, whether there's going to be a call during delta t or not. So in this case, this n is going to be the number of trials. So now let's go one step further. Let's define P to be equal to, note that we don't have any probability here up to this point. This is also very unnatural compared to Bernoulli distribution or Bernoulli related distributions like binomial or geometric, because in those distributions at the very beginning, we got an idea about what P is. And we know what N is, for instance, in binomial distribution, and we simply write binomial distribution with NP parameter pairs. So any variable is going to be binomial distributed in this fashion, we say. Here, actually, we have kind of derived, or we have kind of determined an n, but still it is questionable. We are going to talk about that. And there is no definition of P yet. So let's try to define a P here, at least in wording. It is the probability that, actually I don't need to write it here because it is already written here. Let's see what it says. The probability that a single event occurs during time t. So this kind of pretty much makes sense. During this time, there's going to be an event or not. There's going to be a call or not. This may be, for instance, 1 second, 1 millisecond. How small? I'll come to that in a minute. So in this case, we are going to call this a probability P. So when you make these assumptions, although n is not determined yet because we don't know what delta t is, except it's a small time value, and we don't know what p is, x is going to be equal to, what's that x? Is the total number of calls during time t is going to be binomial distributed with capital N trials and with v probability for each trial. And now here's the trick. Expected value of such a system in terms of binomial distribution is going to be equal to n times p, what we know already. So now the very important point here. Now, how small that t should be, and why does it need to be small, by the way? I said it actually should be small. Here is the important trick. For Bernoulli distribution, there can be only 0 or 1 event, which means fail or success. Note that there cannot be a third option. If you make this delta t to be large enough, if it's large, let's say, then there may be, okay, let's say 1 second. It is physically and it is actually mathematically possible that there may be more than one event, 0 or 1 event. There may be easily 2 calls within that hour, within that 1 second period, or that delta t, which is not small enough. So here is the thing. Actually, there is actually a kind of, well, you can say that maybe it may be not physically possible, but we would like to obtain a mathematical relation that's going to be applicable for all physical realizations. You may say that if one call may take at least 1 second, but we are going to, as I said, we are going to talk about any physical situation which is going to take a finite amount of time. So the only way that to make this small period, or that period of time delta t is going to make available space only for at most 1 event or 0 events. Why? Because otherwise we cannot make this binomial distribution assumption. That's why delta t should go to 0. That's one thing. So in our derivation in the next page, we are going to talk about the case where delta t goes to 0. So this is going to be applicable. This relation, this x is binomial distributed, and expected value of x is equal to n times p only if delta t goes to 0, where delta t is actually used to determine n. And here is the important thing. In this equation, as delta t goes to 0, note that number of trials will go to infinity. So here is the interesting thing. We can liken this process that I tried to talk about here as a Bernoulli process, but only with infinite number of trials. So that's an interesting point. Actually, as the number of trials goes to infinity, then Bernoulli process, what we know already, is going to look like this process that we are going to talk about, which we are actually going to name it as Poisson process. All right, let's go one step further. So what we are going to do is we are going to equate those two equations, 1 star and 2 star. What do I mean by that? Let's go back. It is that equation that we have, where is that one? All right, this one. Expected value of x is equal to lambda rate times t, segment of time. The first equation that we have determined using our heuristics about a Poisson process. And under these conditions, delta t goes to 0 and goes to infinity. This is also valid. Therefore, the expected values should be equal to each other. These two terms should be equal to each other, but only under the condition delta t goes to 0. So therefore, we equate these two terms. And what we do is, since we got, let me go back again. I have already defined p here, but I got no idea what p is equal to, although I have already defined a binomial distribution here. Therefore, I leave p alone here. And now, another interesting point Here, note that this is actually a given quantity, the rate of calls, and t is the segment of time we are interested in. This n goes to infinity number of trials. And as n goes to infinity, probability will go to 0. So here is the complete picture. The Poisson process we are talking about actually is a binomial process with n goes to infinity number of trials with p goes to 0 probability. Note that these somehow actually balance each other. Probability of a call within a very small time interval goes to 0, but there are an infinite number of trials. Therefore, when you multiply those two, one goes to infinity, one goes to 0, you obtain a finite value, which is already obtained by the multiplication of those two finite quantities. Now the question is, how can we use this to come up with a probability mass function of x? If you recall, let me go back. One last time, what we are interested in is to find a probability mass function for this x here. Actually, this is, as you can see, binomial distributed, but under some limiting conditions. Therefore, I use the binomial distribution formulation. Note that the binomial distribution formulation is out of n trials. We don't know, the n goes to infinity, but that's not important. Probability p, we don't know. Actually, it's a quantity which goes to 0, but let's keep it that way. X, these are going to be the number of phone calls that I'm going to be obtaining. N minus x. This is actually, let me write it that way, the number of phone calls that I'm going to be obtaining in time t. Now actually, but this one is the exact binomial probability mass function. Note that this is going to hold only if n goes to infinity. Note that I don't need any other condition because n here is x is the random variable. P is the variable. Actually, you may say that, okay, P goes to 0 is also required. Yes, but actually I'm going to replace P by this relation. So therefore, there's going to be no need for this one. So limit n goes to infinity and x. And instead of P, I'm going to be writing n goes to x and 1 minus lambda t over n goes to x. Now, in this representation, x is the random variable, lambda is the rate of the process that should be given somehow, that should be known to describe this process, the average number of calls in 1 hour. T is the time interval that we are interested in. What is left is this n quantity, which is number of trials, which is actually a number which goes to infinity. Now, the derivation here is actually after a couple of steps, we end up with this equation, which I'm going to show the details of that derivation. Actually, it's pretty much easy. Still, it's going to distract you from the actual momentum of this topic. So I'm going to talk about that in a bonus video. We obtain this result. So this simply says that the number of calls within a t time interval. So therefore, that random variable may be from 0 to infinity, right? All these values, these are the non-negative integers, right? And this countable infinite. So this random variable is represented by the probability mass function exponential minus lambda is the parameter that we need to know. T is, again, you may call it a parameter. It's the time interval we are interested in. Then again, lambda t. So this lambda t as a whole is both here and also here. And we raise it to the power of the random variable and then x factorial. You can actually think about this distribution as exponential lambda t, which is going to be a constant for all different x values. If you would like to compute for 1 call or 2 calls, this is always the same. And this is going to be x. So this quantity will be raised to the power of x. X factorial will give us whether it was the probability of 1 call, 2 calls, and other number of calls. And the expected value of this, note that previously I first derived, or I first introduced the probability mass function, then we have found expected value and variance. In this case, we started with the expected value. Actually, well, we already know what the expected value is. Variance, actually, you can find the variance using the typical variance formulation. And to note that, to prove that the expected value of this distribution, this probability mass function, is actually equal to this quantity, actually, you can use the expected value formulation and come up with the same result, but you don't need to do it because, as I said, we already started with this assumption. All right, now let's solve a question and finish this topic. Number of phone calls, that's a very typical example for Poisson distribution, number of phone calls, but there are other applications I should mention. Well, you should realize that we should have a continuous background, and time is a very typical example for that continuous background. So Poisson distribution is an ideal distribution for time-related events. During some time interval, how many of these events could have happened? Kind of questions. But there may be also other things. For instance, space is also continuous. So in some cases, you may be interested. For instance, let's say that there is an event which occurs for every 1 kilometer. Think about number of accidents, for instance. Let's say there is a very long way and the highway, and there are many then there are accidents realized here for every 1 kilometer, and there's a rate of those accidents. Let's say it is 2.5 accidents per kilometer. Another very important point, maybe I didn't talk about that. Note that lambda does not need to be a discrete value. It may easily be a real value. Actually, because this is a rate, this doesn't need to be equal to x, because actually, so x needs to be an integer, a non-zero integer. On the other hand, lambda is the rate of the occurrence of these events, therefore it doesn't need to be an integer. And also expected value also doesn't need to be an integer, because expected value is not the most typical value or something like this. All right, so I said, okay, if this is 2.5 accidents per kilometer, then you may ask, what is the probability of having, let's say, 2 accidents in 2 kilometers? So now, as you can see, the whole question, if you call this x the spatial direction, you can easily think about this as time and these kilometer as any time unit that you would like. So now the spatial dimension is continuous, and on this spatial dimension there is an event which happens, and note that we should actually divide it into very small spatial delta values. This time it's going to be delta x, and the whole interpretation will be valid. There are in the exercise questions that I'm going to be posting to you, there are some questions related with also the spatial dimension. All right, this one is however related with again time. So number of phone calls that are with office is modeled as a Poisson random variable. All right, on the average there are 4 calls per hour. Now this statement says lambda rate is 4 calls per hour. Note that, as I said, it could have been easily a floating, a real number also. So the first question is, what is the probability that exactly 5 calls within 1 hour will be obtained? So you are going to wait for 1 hour, right? And that 1 hour time, there is going to be 1 additional call compared to the average value. So first, let's define the random variable. It is always important to start with defining the random variable. I'm actually going to emphasize this over again and again. Number of phone calls in, let's say, 1 hour. This is how we have defined it. In this case, expected value of x, for instance, is going to be equal to lambda times so this is going to be t is equal to 1 hour, lambda times t. So when you multiply 4 calls per hour times 1 hour, is going to be 4 calls. Actually, that's very straightforward. Now let's answer this question. What's the probability of exactly 5 calls? So probability of 5 calls is going to be equal to probability mass function at 5, which is going to be equal to, let's go back to our formulation here. We are going to be using this equation, exponential minus lambda t. So it's going to be exponential minus lambda times t is 1. And the other term is lambda times t to the power x. X is equal to 5 divided by 5 factorial. And when you compute, note that this is not smaller than 5 or greater than 5. Exactly 5 calls is going to be equal to 0.156. The second question, what's the probability of 2 or fewer calls in 1 hour? Now the question is, again, we are talking about the same x, number of phone calls in 1 hour. This x is going to be 2 or fewer. Therefore, it may be 2, 1, or 0. So this is going to be equal to probability mass function at these 3 values. So it's going to be equal to then exponential minus 4. Note that it's going to be always the same here. It's going to be 4 to the power 0, 0 factorial plus 4 to the power 1, 1 factorial, and 4 to the power 2, 2 factorial. And this one is going to be equal to 4 to the factorial 0 is going to be 4 to the power 0 is 1, and 0 factorial is 1. Therefore, this is going to be equal to exponential minus 4. 1 plus 4 to the power 1 is 4, and plus and 16 over 2, it's going to be 8, and the result is 0.284. Now let's try to feel what this says. If the number of phone calls is equal to the expected number of phone calls within 1 hour is 4, and if you don't feel very good that day, and for that 1 hour you would like as little as a small number of phone calls as you get, the number of less than or equal to 2 is about 24%. All right, let's go. Okay, first see probability of 2 or fewer calls in 2 hours. Now I have to define this x as a new variable because the previous one is within 1 hour. Number of calls in t is equal to 2 hours. This is our new random variable. And what is asked here is probability of x smaller equal to. So it's going to be again f0, f1, and f2. This time, let's be careful about this. It's going to be exponential minus 4 times 2 because it's exponential lambda times t. So it's going to be again within the common parenthesis of 4 times 2 to the power 0 over 0 factorial, 1 over 1 factorial, 2 times 2 over 2 factorial. And if you do the operation correctly, we have this value. Why? Because in 2 hours, the probability is very much less, having only 2 calls. And what is the expected value and standard deviation of the number of calls in 4 hours? All right, so we need to define another x here. Now, this may seem boring to you and unnecessary to some of you, but please, I really want you to define the random variable at the very beginning of the question. Otherwise, actually, the whole thing becomes a little bit fuzzy or cloudy. Which variable are you interested in? Which variable's probability mass function are you trying to find? So that definition is pretty much important. So what else do we have? Expected value of x is going to be equal to lambda times t, which is going to be 4 calls per hour times 4 hours is going to be 16 calls. Which, as you can see, pretty much makes sense. 4 calls in 1 hour, so 16 calls in 4 hours. And the variance of x is going to be equal to lambda times t is going to be equal to and the standard deviation here is going to be equal to 4 calls. So actually the variance and the expected value of a Poisson random variable is numerically identical to each other. That's an important property. Okay, so that's all I'm going to talk about Poisson distribution. As I said, there's a bonus material related with the derivation of the exact probability mass function. But I think that's all to do related with the chapter 3. Okay, see you.